Hello, this is Math Kimchi, and today we'll be looking at Dijkstra's algorithm. So basically, Dijkstra's algorithm you helps you find the shortest or the fastest or the cheapest path from one node to another, and the best way I can think of explaining it is by just giving an example. So uh, in this example, we're trying to get from A to E and minimize the total, I guess, distance or whatever this number stands for. And I guess we can just say it's distance. And we're trying to minimize the total distance traveled. And you can see that the direct line is the direct path isn't the shortest. For example, from A to C to E is faster because it's 12, and A directly to E is 15. But to do Dijkstra's algorithm, we first have to look at all of the unchecked nodes, and from that we have to locate the smallest unchecked node. And so in this case, the smallest node is going to be A because the rest of them are infinity, and you always start out with the starting node being zero distances, because the distance stands for the distance from the starting node, and the distance from itself is always going to be zero. And also this stands for whatever leads to this node. And for the starting node, I'm not going to put anything. It's just gonna remain x, which can be like none or something like that. But for the rest, it's only temporarily empty, and they'll be filled as we go. So anyways, we found the closest unchecked node with the distance of 0, and from that we have to look at all of A's neighbors. So that's going to be D, E, C, and B. So actually that's all of them. And for example, for B, we're going to do 0 plus 5 and see if that's larger or smaller than the current distance, and 5 is less than infinity, so we do 5, and the path leading to B is going to be A. And for C, there's a similar story, 0 plus 10, and that's 10, and we find the minimum between 10 and infinity, so 10. And also, since we changed it, we're also going to change the previous node to A. And same story here, 0 plus 15 is less than infinity, so we have to change it. And 0 plus 3 is less than infinity. And so, boom. We looked at all of A's neighbors, and now we have to choose between these 4 nodes. So out of these 4, B is currently 5, C is 10, D is 3, and E has 15. And we can see that D is the smallest with 3. So let's look at all of D's neighbors. And if you wanted this to be efficient, you don't have to go over A, but I'm just going to anyways. And so if we traveled from D to A, the total distance is going to be 6, because whatever route we took to D is going to be 3, and we are going to take another 3 to go from D to A. And so if we use this, it's going to be 6, and 0 is clearly less than 6, so we don't change anything for A. And for B, we have the new distance might be 3 plus 1, and that is less than the current distance. So we have 4 as B's new distance, and we are going to have D for the previous node because we used D to get to B's fastest route, at least so far. And we have to look at D's final neighbor, which is E, and the distance from A to D is 3, and the distance from D to E is 7, so that's 10, and 10 is less than E's current distance, so we can replace E with 10. And because we are using the new route, let's also say that D is a previous node, and now we can get rid of D from here. And let's update all of these distances. So B is 4, C remains the same, and E is 10. Now we have 4 and 10, 10. So let's look at B and all of its neighbors. So if we wanted to, we can ignore D, obviously, because that would just be going back and forth. But let's just look at all of the neighbors for now. And if we went from A to B back to A, then that's going to cost 9, because it costs 4 minimum going from A to B, and we're using this route. And then it's going to cost an additional 5 to go from B back to A, and that's going to be a total of 9, and we do not want that. So A can remain the same, and D is a similar story. So it's 4 plus 1, and that's 5 would be the new route, and that the 5 is obviously greater than 3, so we don't change anything for D. But for C, we see that it costs 4 to go from A to B, and it costs an additional 2 to go from B to C. So that's a total of 6, and 6 is less than 10, so we can update this and say that the new fastest node for C is B, and now we can get rid of B, and C is 6, so, and E stays the same. So C is our new cheapest unchecked node, and we see that to go from A to C and then B, the minimum is going to be let's see, 6 plus 2, because A to C is 6 and C to B is 2, and that's 8, and that's more than 4. And for the other neighbor is A, and to go from A to C it's 6, and to go from C directly to A it's 10, and 10 is more than 0, so we don't change anything for A either. And for our final neighbor of C, we have A to C is 6, and C directly to E is 2, so that's 8. And since 8 is less than 10, we put in 8, and we update the previous node to become C. And so we if we wanted to, we could check E again, and I guess we can do that, but even to update like all the rest, we know we don't have to do E because the unchecked is going to be nothing left. But if, let's say, there was another node, and let's call this F, and then infinity and X. So let's have a new node, and the distance, it actually doesn't really matter, but let's just say 2 or something like that. And we know that even if F was here the entire time, it's going to be infinity until this point, and that's because none of the previous nodes would have updated F at all. And if this was the case, then it might be useful to I guess calculate F's distance. But if we were only looking for the path from A to E, then that's kind of unnecessary, but let's just do it anyways. And what we do is we go from A to E, so that's gonna cost 8 at the minimum, and from E to F it's gonna cost an additional 2, so that's 10 in total, and the previous node is E. And if we do that, then we can get rid of E from the unchecked, and F is going to become 10. And I guess we can check all of F's neighbors, but now there's nothing left that's unchecked, so there wouldn't be a point in updating F. So I guess, and there honestly wasn't a point in updating F in the first place if we only wanted to find the path from A to E. But yeah, it was only important if you wanted to look at all the distances for each node. And I hope that was a good enough example to explain. And now I will work on, let's look at the code. So I have already implemented a graph class and a node class, and this is a sample mat I made, I guess, and this is the exact same thing as this except for the F node. And I guess we could add an F node and call it F5 and node 4 and node 5. And actually I could probably have called these like A, B, C, D, E, F, and that would make more sense. But actually, I don't know why I didn't do that. Maybe I'll do that for all of them, I guess, because that just makes sense. B, C, D, So yeah, I just created all the nodes, and basically the graph, you can think of it as this like canvas, I guess, and the graph keeps track of all of the nodes and all of the nodes' relationship to each other. And yeah, create node just creates a node inside of that is a part of the graph, and create uni edge creates an edge, and in here we have an edge that goes from the node start to node end. And the reason why I made this one directional edge, so what I mean by that is you could go if there was a uni edge and the start was A and the end was B, you could go from A to B directly, but not from B to A directly unless there was some other path. And basically you can think of it like this. Like this. So there's basically an arrow, and you can go from here to here, but not the other way. And there's really no use to doing that for now, but I basically was forced to do it because of the syntax. And originally I was thinking of using sets or lists, and actually yeah, sets make more sense, and that would make sense because you could switch two things around. So let's see, let's create a set called S, and let's have like 0, 1, 2 in it, and I hope that's how you make a set. Yeah. And let's have S2 equal to, for example, 0, 2, and 1. So you can see that S and S2 are contain the same things, but they have like different orders. But because of the way sets work, it will say that these two are the same thing. And that really is useful because we can compare like two nodes. So let's say edge 1, and let's just say these connect like 1 and 2, and we want to check if edge 1 is equal to some other thing, like, and we don't know if this is the right order, but it will say true no matter what, and that would be great, except for the fact that you cannot put edges inside dictionaries as the key of dictionaries. I'm pretty sure that's what I mean. So let's say D equals S comma or S and then I don't know, 9, and it's gonna say that sets are unhashable, meaning they can never be keys. And so my only other option was to create a tuple. I don't know why I didn't create a list. Let's see. Let's have L1 equal to 0, 1, 2. And lists, I'm sure you can't change the order around. If you do, it's gonna say that they're two different things. Yep, so even though these things contain the same things, they are arranged differently, so they're not the same things. And but I think you can put lists into dictionaries. So let's say D equals L, and then the value of that, let's just say, is 0. I'm just pulling random numbers. Oh, we have to do L1. Oh, and I guess lists are unhashable as well. So really, sets, tuples are my only options, because T1 equals 0, 1, and tuples, the order matters, but at least you can make them into, for example, key of a dictionary. So yeah, and that works. And if we did D and look for T1, it would give you T. But unfortunately, if you do T2, it won't work. Hopefully this means that the key isn't in there. But yeah, oops, I don't know what I did. It'll probably fix itself. Oh yeah. But yeah, so the way I got around with that was that I created a tuple, and now basically any time I want to create an edge, I'm just going to do, for example, if I wanted to create an edge from A to B and it goes both ways, I basically just create something from A to B and it's an arrow, and also from B to A, and it also only goes from B to A. And because I have both of them, it basically works. And yeah. And I'm pretty sure each edge is stored inside of the graph's edges as a dictionary, or inside a dictionary as key value pair, and the key is going to be the node start and node end, and the value is going to be distances. And when I create a bidirectional edge, I basically just create two identical edges, except for the fact that the start and ends are switched each time. And whenever I create a node, I store the graph that it's in, the value, and the reason why I have a value is to make printing easier. And the children function, what that does, or the children stores all of the the children stores all of the edges. So for example, it might look like 0, 1, 0, and 1, 2. So basically there's an edge, or wait, if this was node 0, then we'd have 0, 1, not 1 0, because we're only looking at when this node is the, I guess, the parent, and it would be like 0, 2. And what we can do then is do self.graph.edges, and then, or actually no, if these were like the edges that 0 leads to, then there would be 1 and 2, and this just is the stores everything that all of the nodes that this node leads to. And so what we could do is do self.graph.edges, and then bracket, over parentheses, self, so this node, comma, for example 1, and it will display a dictionary, and it might say something like this, you know. So yeah, I hope that is pretty easy to understand. Now let's actually work on the algorithm itself. So before we actually work on the Dijkstra's algorithm, we can create a distances function, and what this is it takes the starting node and it probably just returns all of the, like, a list of sets probably, and the set contains like the node and the distance from the starting node. And so basically, yeah. Sorry, there's something in my mouth. And I guess to get this started, we can have unchecked edges equals graph dot edges. Yep. And wait, or no, unchecked nodes. Yeah. And that's just graph dot nodes. And we can do that, or we can have a dictionary, but I guess we can have something called all, or like this. And this is going to be, or like temp distances, and this is going to be what we think the distances are, and at the very end is going to become right, and this is gonna contain all the nodes. Wait, I hope dictionary comprehension is a thing. So graph.nodes for C and H 0, 2. So it seems to be a thing, and maybe you can do something like this. Alright, so we know that unchecked nodes, oops, yeah, so we can go through unchecked nodes and node, comma, and yeah, so this is the key, and the value is going to be the distance, and I think this was a thing. Int. Oops. Infinity. That's about maybe float. Yep. So float of inf is probably the way to have infinity inside Python, and it'll be as a float, and the distances equals, yeah, for now everything is infinity, but of course we have to make the start equal to 0, and let's say while unchecked nodes doesn't equal to just an empty list, closest unchecked equals min, and then unchecked nodes, and then we can actually have something called key, and this is the way min function checks what is the smallest, and we can have a lambda function take in node, and it returns so it should return the distance, and so we can use temp distances of node, and hopefully that works. And after that we look at for neighbors in closest unchecked, oh wait, when we have temp distances, we also need to store the previous node. So I guess one way we can do that is just by doing this and having by doing that. And now we just have to remember that for the syntax. And for this, right now this is gonna return, for example, float inf comma none, and so we only care about the 0 thing, so we do that. And for neighbors in closest unchecked dot let's see, children, maybe we should call it children, but I don't think it really matters. Yeah, so for every neighbor, let's say from C to E, so we have to look at the neighbor's distance. Oh, and another problem is, what do we do if they're the same distance? And I don't think it really matters if we choose the newer one or the old one, but I'm just going to say to choose the old, just keep it the same way unless we absolutely have to change it. So if neighbors temp distances, neighbor, actually this should be singular, 0 is greater than, and this is the case in which we have to do something. So if it's an equal to, it's gonna be false, so we don't do anything if they're the same thing. And that just makes sense in my brain to not change anything unless it actually matters. And you know, I'm pretty sure that's gonna make it slightly faster as well, but for now we're not really going for speed, we're just going for what's like the most elegant, I guess. But we do if temp distances, neighbor, so the distance of neighbor is greater than closest unchecks, or the distance, so temp distances closest unchecked 0. So this is our current distance plus the whatever it takes to go from closest unchecked to neighbor. So how do we find that? Let's see. Yeah, we probably are gonna need graph dot edges and then the start is going to be closest unchecked to temp distances, and we want the dist from that. And yeah, so this is the old, for example, if we're going from C to E, and C is our current node and E is our neighbor, this first thing is going to be E's current number, and this thing is going to be A to C, so 6, and this thing is going to be this thing from here to here is going to be from C to E, so that's just 2. And in this case we wouldn't do anything because they're the same. So, but if they weren't, let's say this was infinity, then what we do is, this is x, what we do is we say that C alright, so we have to edit temp distances of neighbor equals, and we need 2 things, and I guess we should make these, put this in a list. And the first thing is the new distance, and that's really janky. I guess we can say dist equals that. That's much more elegant. New dist comma, and the second thing we need is whatever leads up to E, so that's going to be the one we're checking right now, closest unchecked. And honestly, I think that is it, and we just have to return temp distances. And so first what we do is we call distances, and distances actually these just short for distances, and let's say distances equals to a graph, and this is going to return something like A, and then it's gonna be like 0. Actually, yeah, let's see what it would be for this from what we manually did. I'm pretty sure this was an 8 and then a C. So for A, it's gonna return none, and for B, it's going to return 4D, 4 and D, and blah blah blah. Oh, I can't do that. But anyways, what that's gonna do after that is this function was supposed to do something else, but yeah, before I created this video, I tried to do the same thing, but I used a little different syntax for what we returned. So I guess a better way to do this is by doing print n, and this is the node, and we have ds of n, and then honestly, yeah, we have that, and let's shoot. So where's the error? And the error here, and let's see what the problem is. So new dist. Oh, also, I just realized you have to get rid of dot remove is the syntax, I believe. It's either remove or pop. One of them gets rid of one of them gets rid of it using the index, and the other gets rid of something based on the, I guess, the value. But we still have the other problem, which is so closest unchecked is definitely not. You know what? I'm gonna print closest unchecked just to make sure that it's not. Yep. So it's a node and not a dictionary. So our problem is going to be at here. Really? Let's see what happens if we remove. I'm just gonna hash it out. So apparently it didn't completely break. Oh yeah, and we have to print the values of each. But back to what we were doing earlier. So we have there's a problem with the fact that it thinks this is a dictionary. I'm just gonna check if this is the problem. And apparently it is. That is weird. Wait, so let's I don't know why that's happening. Oh yeah, what if we did something like this? It's clearly not a dictionary. So maybe there's a problem with oh. Wait, I think this isn't supposed to be temp distances. Oh yeah, this is supposed to be neighbor. Probably. Oh, so it looked like something. So that problem was fixed, but there's a problem with the printing, and I'm pretty sure it's because we set this to none, and it's looking for that. So I don't know. Maybe we can use if statements. Yes. So I guess you can't use if statements inside of. Is that? That's annoying. Maybe you just need an else statement. We close that one. So something seemed to have happened, and so we have all this is from this, which we can get rid of. And oh yeah, by the way, this is just if this is none, or if this isn't none, and if it isn't none, it's probably just going to be a node. We return its value, and otherwise we just have none. We just print none. I'm really glad that worked, but anyways, we have a 0 9. Yeah, so it gave us an answer, and let's see if we agree with it. So a to 0, yep. B is 4D, yep. C 6B, D 3A, E 8, C, and F. Ooh. Oh, there's a. You just have to edit the distance here, and yup, I think everything's working perfectly. So now, I guess we can also make distances more efficient by only doing this if neighbor isn't yeah. So maybe we can have like something here. It's like if neighbor is not inside of this, then, or like only run this if not neighbor inside unchecked nodes. But honestly, I'm not sure if that 100% works or not, and so I don't really want to risk it. But yeah, now we just need the actual Djikstra, and let's have start, end, graph. And so what we do is we have dist equals distances of start, or actually yeah, maybe we should make this its own thing without relying on Djikstra. So wait, yeah. Even if we do reach at the end when we haven't checked anything, we can't return it immediately because we wouldn't be sure if the first path we find is the shortest path. Wait, no, we can be sure because I think the way that Djikstra always guarantees the fastest path is by looking at every single possible path by length. Oh, wait. Or maybe not. I don't know. I don't think it's wise to risk it because I thought Djikstra worked is that Djikstra always looked at the shortest possible path that starts with A. So basically what I'm saying is that this is the shortest, these two are the shortest possible paths from A, but I just realized that that's not necessarily true because this is not one of the shortest paths, and this is. So maybe maybe if we looked at it recursively and went like that and then that. But yeah, I guess it's never guaranteed that the first path to the end is the fastest. So I guess we can just use distances. So yeah, dist equals distances, and then we have start our graph. Let's see, we can do this. And so from E we go to C, from C we go to B, from B we go to A. So return path equals temp node equals this end. true while temp node are equal to Djikstra start. We do path dot append temp node, and then temp node equals temp node dists one return path. And we're probably gonna have to add the start or the end like outside of the while loop, but let's just see what happens. So actually I'm just gonna A to E. Oh, use to print DS. Oops. Print for so E C B D E C D A. Yeah, so we just need to make it add the last one at the end. And I guess we should make this the reverse order. And I think this is the syntax to make it reversed. Oops. Oh. That's it. A, B, D, A, D, B, C. So A, D, B, C. That sounds pretty right to me. And, you know, if we just do E to A, we should get the same result, just backwards. And if we go from A to A, we're probably gonna have an error, because wow, that is surprising. I thought we'd have to create a special case for A, but we don't, and that's pretty great. Yeah, so I think that basically covers everything and every like possible case. I hope it. Well, I guess we also have to check if if it even is possible, but I don't know, that can be for later, and for now we just assume that it is a possible solution to solve. And yeah, I guess that's it. That's pretty much it for Dijkstra's algorithm, and thanks for watching.